Thank you. Hello. Today I'm going to talk about two topics. One is on how we accomplished in situ visualization on large-scale simulation and extending that work into building digital twins and be able to manipulate those simulations inside the digital twin, and how we leveraged LLM to achieve those aspects. So I'm Krishna Kumar, I'm faculty at UT Austin, and this work is in collaboration with Paul Navratil at TAC and Andrew Solis and Greg Abrams, and our student Sean McLean, who was at the Odin Institute. So starting off, our focus was, why do we need ray tracing in scientific visualization? This is a view of the Earth's interior from the Kronos group. You can see how by highlighting individual aspects and doing shading, we can elucidate insights which were previously not available without those ray tracing aspects. So you can see that ray tracing helps not just in making great animations in movies, but also in scientific simulations. So I'm mainly in civil engineering, so working on natural hazards and other construction aspects. So in civil engineering problems, we do use quite a lot of simulations, and it is important to visualize them quite realistically. So here's a conveyor analysis, which is done using discrete element method. This has about a few 100 million particles, and you can see that by rendering it, we are able to clearly show what is the mechanism that is happening. And this is the very popular 60 million golf buckshot problem. But it is not just in particle-based system. In continuum systems like material point method, which we will discuss soon, we do use quite a lot of visualization in conveying the hazards. And it is essential when you're conveying hazards like landslides to understand what the effect of the runout would be. And if there are communities downstream, we need to be able to clearly communicate what that risk is and help them make suitable decisions. But these type of ray tracings are usually expensive. They happen post-hoc analysis. So you perform your simulations, store your results, and then go do rendering of those simulations. So these are time consuming, and our first goal was, how can we make these ray tracing more real time? But the first aspect is still continuing on where we have been using these ray tracing. We've used it in understanding concrete flows, because this is critical in understanding how a particular concrete gets pumped between those reinforcement bars and whether it clearly covers those reinforcement bars. So you can see how well we can communicate that without ray tracing. And this is achieved all using ParaView with Intel Osprey plugin enabled. So you can see how different concrete mixes, whereas if you're just doing typical rendering, we won't be able to see that detail. So our goal is to take this really realistic rendering from a post-hoc way of doing it. That is, you would typically run a simulation, store your results, then use ParaView or other type of tools to do then the rendering of your simulation, to do it in situ. By which we mean that we want to make the simulation and visualization run both in parallel. The simulations are being taken over and being run on certain number of nodes, while the rendering also happens live in other nodes, so you can clearly see what the results are while the simulation is running and probably make changes to it. What are the challenges we have is, typically the visualization is sequential. You start with input and boundary condition, run your simulation, then post-hoc do that visualization. We want to break the cycle and be able to look at the results while the simulation is running. And it is probably pretty reasonable to do it when you're in 100,000 particles or 100,000 elements that you need to render. But as you get pushed to more the exascale side, the input-output becomes a bottleneck. We don't write out the output at every step. We tend to write it at finite number of steps. So like when we are writing huge simulations with 50 million or few 100 billion particles, then you're going to write terabytes of data. Then we need to be able to read those terabytes of data and visualize at these discrete time steps. We're probably losing some of those useful data as we only save it at those time steps. So what if we can break the cycle and do in-situ visualization with live feedback and be able to also visualize the same results at different locations? Let's say we are running the simulations in the supercomputer at TAC, then we should be able to visualize the results across the US and people connecting to our system and be able to see that. So experts who are looking at the landslide effects can make decisions, and also like decision makers and policy makers should be able to look at those real-time rendering and make that decision. Because we're going to be dealing with closer to exascale computing, we want to be able to do all of this in a parallel chunked way. So we need to be able to run rendering in real time and distribute it across multiple systems. So the goal is to do a large-scale landslide simulation. So we are going to replicate the Oso landslide that happened in Washington about 10 years ago. And we're going to do that using a method called material point method. The material point method represents the system or the domain as material points. The material points carry all the information, and it's going to have a mesh as well, where usually the system is solved and the information is projected back onto the material points. The material points can go through the mesh, so we have to deal with a hybrid Eulerian Lagrangian system where we have a fixed grid and the moving particle that goes through the system. And typically, we are going to only render the particles in the system and not that grid itself. And one of the things you notice here is that the landslide topography is really complex. And when you have these complex sort of topography, you need to be able to have unstructured mesh. So how are we going to deal with those in terms of parallelization is another challenge. We're going to be using TAC Galaxy. This is the work we did with Paul Navratil and Greg Abrams in enabling asynchronous ray tracing with the NPM code. So we had an integrated end-to-end communication system that allows us to send the simulation data running on certain cores to the visualization engine, which is Galaxy, but Galaxy is built on top of Intel's Osprey and Embry, and we are leveraging both of those to be able to do this asynchronous ray tracing approach. So we'll talk about a little bit of the challenges we had to go through, but we used the Intel Osprey library extensively in defining our materials. This was our initial showing that how we can simulate like transparent materials, but we are going to have a few billion particles or close to 50 million material points when we are simulating our landslides. So we set out what the texture coordinates should look like, what the displacement profile should look like, and then did our first rendering of our landslide mechanics. So this is looking at a picture which is zoomed in view, and you can see that we have enabled global illumination in one and with and without global illumination. So we are trying to have global illumination enabled in doing the entire simulation, so we can see where individual material points are in a landslide. So having enabled those, this is our first rendering of our big Oso landslide simulation. So this is about 1 mile by 1 mile in diameter, in the width, and it has about 50 million material points that we're trying to render. So we had 16 nodes on the TAC supercomputing cluster with Intel Cascade Lake processors running the simulations, while 8 MPI nodes were doing the visualization or rendering using TAC Galaxy. So the biggest challenge is that when you're doing these huge simulations, we need to be able to divide up the domain, and that's typically done using domain decomposition, and be able to partition that, run the simulations, and also do a distributed asynchronous ray tracing with TAC Galaxy. So our first step was to do domain decomposition of the NPM simulation. So we use the graph partitioning mechanism. Graph partitioning allows us to look at how many material points are in a given cell, and then they are going to evolve over time, and we are going to use the graph partitioning to distribute the workload. We do the dynamic graph partitioning, especially in landslide, because initially you're going to have a source which is closer to one region. So we would have a different type of load imbalance compared to as the landslide progresses through the mesh, the number of material points in each cell is going to vary quite dramatically, especially if the runout is about close to a mile and the simulation has about 50 million material points. We need to be dynamically doing this process of rebalancing. And we do this, and here is us showing the scaling results on the Frontera 8280 Cascade Lake processors from Intel and how our scaling performs. So the blue line is our theoretical performance of scaling, and you can see that closer to about 7,000 cores, we have pretty much a linear scaling of our results. And this is our NPM simulation. So one of the things you notice is when you're doing an NPM simulation, like a landslide, so here's us showing how that landslide would look like. You have an unstructured grid where the landslide materials can go through the system. And initially, you might distribute the blue particles here and distribute it this way. And you can see that the particles can go to another compute domain or the MPI domains, and we need to be able to rebalance. Not only that, the mesh is unstructured and the material points move through the mesh, the galaxy partitioning is much more rectilinear. So we had to be able to transfer particles using two meshes, one for the NPM simulation, the other for the galaxy partitioning. And galaxy is our ray tracing engine, which allows us to do these interesting visualizations. So we had to be able to communicate between the NPM simulations and the galaxy ray tracing. We used an end-to-end communication system that allows us to send and receive particles through the galaxy raycasting tool. So this is our first rendering. This is the in-situ rendering of the NPM simulated after 50 seconds and after 74 seconds. The entire simulation in the real world took about 2 minutes. So the entire landslide ran out for 2 minutes for about 1.6 miles. So it's about looking at it after 50 seconds of that run out, you can see where the particles evolve. And after 74 seconds, this is enabled to galaxy, and we do ray tracing with global illumination. And these are all running in situ. So our compute is running on 16 nodes, while our visualization is running on 8 MPI nodes on top. The problem is when you're doing these large-scale simulations, we had to do quite a few runs in deciding where to place the cameras because you're doing everything in situ. You're trying to do the simulation and visualization in real time. So maybe our rendering may not be right. We don't know what the maximum runout is going to be. And also, where should I place the cameras because I don't know where the simulation is going to take the landslide runout. The landslide runout can go in a completely different direction compared to what we were planning. So our initial part of the work involved us doing quite a lot of these simulations where we had to decide and change camera angles because the camera angle was not accurately capturing, or the contours we have is not sufficient enough to render the entire displacement runout. In most of the simulations, we don't know where the interesting things are going to happen or what the range of values we are going to get. So the way we want to proceed with this is how can we bring in machine learning type methods which can identify where interesting things are going to happen and then decide how we are going to visualize those systems. And that's where we are taking the in-situ rendering to the next step. And in order to do those type of predictions, we leverage something called a graph network simulator. The graph network simulator allows you to replicate the entire simulation. So here on the left, you see a typical material point method simulation, which is shown as reality. And the graph network simulator is our approximate surrogate model for our NPM model that runs it closer to real time. The goal of this approach is basically to have a surrogate model which can run much faster than real time and be able to inform our in-situ visualization oracle where to place the cameras, how do we want to set up the values so we can capture all the interesting features in real time. So how does the graph network simulator work? The graph network simulator basically takes the entire domain, discretizes into individual nodes in a graph, and the edges model the interaction in the graph. We basically take the previous n time steps to be able to predict what is going to happen in the next time step. So all the work which I'm showing here are public open source codes you can check out on GeoElements/GNS or CPGeo/npm and Tag Galaxy websites, and you'll be able to use all these resources. So once we construct the graph, we then use message passing. Message passing is basically propagating that information from one node to its neighboring nodes, and we do that up to n steps, and finally we do a decoder step where we go from the latent space in the graph finally to the dynamics. By training the graph network on multiple simulations, we are able to generalize it really well. So this is a prediction of a graph network simulator where the graph network simulator has never seen a simulation like this before, but it is able to run it in faster than real time. So here it's a 3D simulation, but you're looking at a 2D view. What would typically take on two nodes with Cascade-like processes, 2.5 hours to run, the GNS will be able to run something similar in roughly 20 seconds. And this speed up means that we are able to use these graph networks as a proxy to find out where interesting aspects are going to happen, place our cameras, and do real-time rendering. Not only that, it can also look at models for which it has never seen the geometry or configurations before and be able to reasonably replicate. So it's reasonably replicate. We are not trying to do an exact match because we just need to know where interesting aspects are going to happen. So if you look very closely to these systems here, what is happening in reality in NPM would be different from what is happening in the graph network simulator. But with the accuracy is around somewhere between 98 and 99% of our simulation, which is reasonable for us to set up the in-situ visualization pipeline. So what we do in terms of developing the in-situ vis pipeline is train a graph network simulator on multiple simulations, and these can be small-scale simulations on which the graph network is trained. We predict the dynamics using the graph network simulator, then identify where to set up our camera configurations, what visualization parameters are interesting, whether it's stresses, strains, or displacements, set up what will be the maximum values of those ranges, and then do the NPM simulations with Tag Galaxy, which allows us, everything is now set up. We know where to change our camera angles while the simulation is running, because initially we are interested in headscarp, and maybe as the runout progresses, we change our camera angles to be able to capture all the dynamics that are interesting for us. And once we have done this, we are able to set up our in-situ visualization going. So here's a video of what the in-situ Viz Tag Galaxy rendering simulated. So this is still 16 nodes on Tag running the rendering simulation, and 8 nodes running the rendering aspects of it. So we are coloring it based on how far the particles, in this case, the soil and the runout ended up, and that allows us to clearly see what the runout was. And there was a village down here to the right, which got submerged because of this landslide. So we were looking at how is it effectively, can we communicate what the risk would be in such traumatic situations? Okay. So in terms of the workload, because we had to do all of this asynchronously, and you knew that the NPM simulations had dynamic domain decomposition, and we also had to transfer the information of those particles to the RAM to other compute nodes which are running the visualization. You can see the amount of compute time that took. It is 10⁻⁻² seconds. So a very little time was taken in terms of communicating the particles. So we had to distribute the particles from the NPM simulation to the right meshes in the Tag Galaxy system. The communication took a little less time almost like 1/3 of the time it takes to do the actual rendering. And this is for 15,000 particles. The scaling was almost linear in terms of getting to about 50 million material points that we simulated. So by combining our machine learning approach with the ray tracing, which is built on Osprey and Embry, we were able to leverage in-situ visualization and bring in the dynamics of real-time visualization with machine learning accelerated feature identification. Extending on the idea of machine learning, we wanted to extend this to see, okay, we have a simulation which allows you to do real-time rendering. What if we could go to field, look at construction sites, be able to build a real-time digital twin and be able to manipulate that? So the manipulation part is what we are currently working on in combining our current technologies. But this, I'm going to talk about differentiable rendering and how we're going to use large language models in achieving an automated construction of these digital twins. So if I were to model an entire city or a construction site, I need to be able to start from modeling individual sensors. Here we use like physics-based ray tracing methods. So we start by modeling the Lidar sensors, which are modeled as point clouds, which are easier to aggregate and construct a single scene from multiple sensors because you can just overlap them together and construct an entire 3D scene. We can also simulate different camera angles, lenses, and environments. So here's us trying to simulate a city scene with a Vespa in here and making sure that we capture the correct lenses for the cameras. And I want to show that we are able to compute by using a physics-based ray tracing engine. We are able to not only look at the obstacle, but we are able to look at the obstacle in different lighting conditions and different focuses. So these are varying the camera specification and the ambience, and you can see how we are able to synthesize the same scene under different conditions. The reason why we need to do this is as we have digital twins which are constructed in real world, we are going to be done during rain, haze, and be able to identify every object and manipulate them. And that's one of the reasons where we start by, okay, let's model the sensors and go after modeling every single aspect of it. And we wanted to see how well the current object deduction methods like YOLO works. So here we take a car model, have it under different lighting conditions, and this says like the probability that this is a car kind of varies as your lighting condition changes, but it allows us to generate realistic lighting conditions and see that in all these cases it was able to identify the cars. And this is a good scenario where it's a simulated condition. There's no other objects in the scene, which can create adversarial connections to it and misidentify or misclassify the object. But we know that our method works. We are able to generate ray traced, realistic looking objects and be able to identify what those objects are. Now let's come to looking at objects under different lighting conditions. So we are simulating two cases, one where the lighting conditions is a perfect daylight condition, and another condition where it is a nighttime condition. So in both conditions, you can see that here it's able to identify almost all the objects very accurately. And the motorcycle becomes a little bit duller, but it identifies all the plants. But as you go from day to night, the object detection becomes difficult, or the precision or the probability at which it is able to identify these objects kind of drops. And as we go through different scenes, you can see that the object detection mechanism, which is our AI machine learning approaches, also might fail for different reasons. So here is YOLO V7. So remember the condition where we generated different lighting conditions. What we then did was to simulate a rain and added the rain dynamics into our simulations and re-rendered those. And as we added rain into our simulations, you can see that now that object, which was correctly identified as a scooter, is being misidentified as a bench or even as a fire hydrant with 28% probability. Although the probability is low here, it is unable to identify in any of these other scenes, which we can clearly see at least in a little bit of lower light conditions, but the current state of the art, this was a little bit ago, LOV8 and other methods, the state of the art CNN still fails to identify these objects. What was interesting was as we were modeling different city scenes and trying to do ray tracing and do object detection, and our next step was to automate and construct this entire our simulation to a digital twin, is we simulated an upscale neighborhood and a low-income neighborhood. And in the upscale neighborhood, the one I want you to bring your attention is the stop sign. And it says it's a stop sign with 30% probability, and it doesn't even face the direction you're looking at. This is a low-income neighborhood, and in the low-income neighborhood, what you notice is that the scene is a lot more complex. It's because of different lighting conditions, and so the shadows from these high-rise buildings are affecting the results, but it completely misses the pedestrian signs. There are multiple pedestrian signs. We didn't change the CNN object detection algorithm, but you can see that the number of objects identified in a high-income neighborhood, which is clear compared to a low-income neighborhood, it completely fails to identify critical objects. So we need to be able to identify objects in a construction scene, which is going to be a lot more complex because we are looking at what will happen while the city is being constructed. There's going to be a lot more chaos in that system. Things are often under construction. It's hazy. You won't have full objects and be able to do a real-time digital twin construction. So how do we want to do this? We want to be able to construct a digital twin by not just constructing a digital twin. Maybe you want to explore what that digital twin has, or use a combination of drones and simulations and digital twin in identifying objects. Oftentimes, you want to be able to know if a given construction site is on track or it is lagging behind. So we want to be able to just say at a construction site, find me the red ladder. In this case, the red ladder is here and also on the third floor. Or explore inside the structure. And you can even ask more complicated things to say, okay, here's the construction site, go build a digital twin and compare it against the BIM model, which is a building information model, and see whether the construction sequence is ahead or behind schedule. And it is a lot more easier for engineers at the site to just talk to these systems. So just talk in a natural language and say, explore the inside of the structure and build a digital twin, or complete loop around the perimeter of the construction site and build a 3D digital model. And this is, of course, you guessed, is if you want to talk natural language, you need large language models like GPT or Llama, and we are going to leverage those in combining it with the digital twin construction process. Very briefly on the language model, language models have exploded onto the scene, but basically it's a text prediction system. I'm giving a civil engineering example, but you don't need to be a civil engineer to understand this, where we have a geotechnical engineer who looks at construction sites and looking at foundations. They discovered a particular site in a dry soil in Arizona. So the keyword is dry soil in Arizona, and we asked GPT model to predict what is the sequence of the next sequence of words, and which is what a language model usually does, takes the sequence of words we have and be able to predict what is the next set of sequence. And here it is saying it was not suitable for construction because it's a dry collapsible soil, so naturally it was not suitable for construction. What's interesting here is it's always picking the most highly probable word. So once it picks was, which is 76% probable, it goes to the next probable word, which is not, and then suitable for construction. And this happens when you have set a temperature setting to be 0. That is to say that don't be creative, just pick the most probable one. And every time if it gives out the same sentence like was not suitable for construction, we find that bit robotic or monotonic. That's why we want ChatGPT like tools to be a little bit more creative. And here we use GPT and we set the temperature setting, which is the creativity setting, all the way to 1. Typically, ChatGPT has setting of about 0.7. We tune it all the way up to 1, so we are asking it to be highly creative. And in that case, your GPT model is now trying to say it was. So in this case, it picked the most probable word. And instead of picking not, which is the most probable word here, it picked out something which was less probable. So it said was highly, and once it went highly, it went saturated. So again, remember, we're talking about a dry soil. It now says dry soil was highly saturated with water. It was completely dry side is filled with water, is what GPT model says. So it definitely hallucinates whenever you make it very creative, but you also wanted to be able to look at construction sites, engineering problems, and be more deterministic. So of course, we can set the temperature setting to be 0, but we need to be able to leverage and make sure that these language models don't break down when we are trying to do complex engineering tasks with it. So we are going to use large language model agents. These are agents which are going to be decision makers. We are going to give them certain parameters. We are going to allow the agents to do planning, where they are going to break down the large task into smaller subtasks, and then refine each task as it observes certain things. We need to, excuse me. Okay. The next part is we need to give it some memory, because the language model will only remember what it saw in the previous step. So we're going to give it a long-term memory so it is able to go fetch all the information it needed to be able to complete the given task, because it's going to break down a large task into smaller tasks. So it needs to remember what it did 2 steps before. So we basically use a database giving language models the ability to access memory from different chunks of the workflow. We are also going to leverage tool use, because language models by itself can't do everything. So we are allowing the language model agents to have access and also use external tools. So it can command drones to say, go fly in a certain direction, so that it is able to get better views of what is happening. Okay. How does an agent work? So we can ask GPT type model, like calculate a particular mathematical formula, and it gets it completely wrong. So instead of trying to ask language model to do calculations, why not give it a calculator? So in this case, I want to know what the calculation is. Instead of it doing the calculation by itself, it outsources it to a calculator, which then takes the input, gives it the output, which the math calculation engine can take over. And then once it gets the result, the LLM agent can decide what to do with it. So in a construction sequence, this is going to be a lot of different tools that it needs to access. So we want to be able to build an autonomous system. And here we are going to leverage CPU-based rendering. We are building an entire model, then leverage the CPU-based rendering to construct a scene. We're going to run simulations through the scenes, like flying drones through the scene to identify different areas, lighting conditions, do a full 3D construction. And once we show this is demonstrated in these 3D models or synthetic models, we're now planning for a real-world demo of what we are building with the digital twin construction. So we need to be able to construct the 3D scene from experimentation. This will require us to simulate the complex environment. So you can see this is a cleaner environment compared to an actual construction site, but quite a lot of structures are unfinished. So identifying those objects will become difficult. But there is also quite a lot of chaos that is happening in a construction scene. In order to do this autonomous drone exploration, the features or requirements of this autonomous system are we need a vision system. So this is the ray tracing we've been doing before, but we are only going to look at it from a camera point of view. We are going to add a Lidar system, and this allows us to place objects in 3D, allowing us to figure out what the depth is. Again, we are doing it with ray tracing, where we saw sampling a point cloud. And we are then going to combine this with localization and mapping to understand the location and the world we are looking at. Then finally figure out how we are going to plan the motion of these drones. And finally, give a human agent an interface. This is where we are going to integrate it with a large language model agent to look at the results. So going through the vision system, it's the same CPU-based rendering system that we've shown before. So we have a camera, we're looking at a 3D scene, and you're looking at what that image would look like as you do a ray tracing given a particular light source. Here we're doing all of those in a well-lit daytime condition. And we are also going to move the object around and decide when to regenerate those images, because these images are being fed live from our drones. And that will be at a finite time intervals so that we can re-render the whole scene or partially re-render the scene if the drone has not moved significantly. The next part is the Lidar. We're going to simulate the Lidar to understand the depth of where our drone is and where it is recording it from. This allows us to identify specific camera locations, to record all the intersection of lights and the interactions with other objects. But Lidar gives us a flexibility because it allows us, if I have 2 or multiple drones, I can put all the point cloud together, then do a method like DB scan to construct different parts of the object, and then combine those 3D scenes. And we basically remove roughly 90% of the point clouds for efficiency purpose so that our Lidar system can be really fast. Finally, we use PlaneSLAM. This is basically taking our 3D Lidar SLAM algorithm, extract planar features. So most of the construction sites have like walls and floors. So we are going to identify those planar features. That becomes a lightweight, real-time localization and mapping algorithm. So we're going to generate the point cloud. Then we're going to do meshing, cluster those, extract the planes, register those planes, and that allows us to then go ahead, map our trajectories for our drone through these complex scenes. And that takes us to the next part, which is the motion planning, where we are going to rapidly move the drone to identify different scenes here. We are leveraging the rapid exploration random tree algorithm. RRT is an algorithm that is designed to efficiently search non-convex high-dimensional spaces by randomly building a space-filling tree. So the way we work is we generate a raw point cloud data, which is generated from the drone location, converted using the PlaneSLAM, which I discussed before, into lightweight objects. And once we have these lightweight objects, we are going to do the RRT algorithm that generates random paths, starting from a starting point and destination. Here, I'm specifically giving what the starting point and the end destination is. And based on that, the final path gets chosen. We're going to fly that drone, capture that system. But that involves me telling where to start the drone, where to end that zone. Basically, I'm telling it, this is the starting location, XYZ, and this is the target location, XYZ, and the RRT figures out what is the trajectory it needs to take to do that. But we don't always have this because we don't know where that location is. So how can we control the movement of the drone so that we know how to identify objects in our scene? Our solution is going back to the vision system. And this is before like GPT-4 vision what came along. So what we do is basically use the vision system with a grounding dyno, where a user basically interacts with an autonomous system and they can easily tell the drone where to go and what to do. So we use grounding dyno because it's an object detection model that combines what the image is showing. So the visual content of the image is identified, and then we give the image and the text prompt to identify specific things. So we can do referring expression comprehension, REC, which involves identifying and localizing a specific object or region within a given image. So this leverages our vision-based system. Here's how grounding dyno works. You can of course, use something like YOLO and identify all the objects in the scene, but Grounding Dino allows you to specifically ask for, okay, where's the red box above the door? And it will be able to identify where the door is and identify that red box above the door. And this is useful to identify a particular object in our construction scene and say, find me this object, and then use the path planning for our autonomous drone to be able to drive that. Or another example to be, say, is like wine glass on the far left, and you can see that it is able to identify the wine glass. And finally, you can also even say man with sunglasses, it identifies this, and then you can be more specific and say, okay, man with sunglasses and blue shirt, and it will be able to identify the person on the right. So now we have the 2D scenes, but we need 3D reconstruction from what the drone sees as a 2D image. This is where we go from the image to use Make It 3D. Of course, now we have technologies like neural gradients fields and Gaussian splatting, which allows you to construct 3D objects from 2D scenes, which we're currently working on. For this work, we use Make It 3D, which takes our multiple 2D images and convert it into a 3D mesh. Once we do a 3D mesh, we then do a similarity search on that mesh to identify that 3D objects. So our similarity search works this way. We want to find the red ladder on the right. We use the DB scan to perform clustering on the generated LiDAR scenes, and we can have multiple LiDAR scenes generating and clustered together. Then we do a similarity comparison of our target object. So once we have the target object, we do a Make It 3D, and then use that Make It 3D object to develop a bounding box. And then using those bounding boxes, we are able to locate in the physical world where that particular object is. This is to find a particular object, but we can also be able to identify this particular object and place it in 3D so that we know where that object is, or even compare it against a building information model, which allows us to see whether a particular construction site is behind or ahead of the schedule. And finally, to go from 3D objects to see what the reference silhouette image is, we leverage differentiable ray tracing. This is a simple example of differentiable rendering where we do mesh-based rendering. So here's the 3D object that we have. And let's see if this is our reference silhouette. We have a starting point and we calculate what is the gradient of this reference silhouette to what the starting point image looks like. And if we just use purely image-based loss, we can iteratively optimize. You can see takes about 50 iterations to exactly place that object in 3D so that we can recover back this reference silhouette. We do this in ray tracing, so it's slightly more time intensive, but it allows us to place these 3D objects with the correct texture and lighting, so you're exactly identifying where that 3D object is. We do this only with camera losses, but what we found out was if we can combine the camera loss, which is the image-based loss, with the point cloud data, our loss converges much quicker, and it is also able to place those objects much better than just using image-based loss function. So combining all these components, we put those all together with an LLM agent. So here we have an LLM agent. We use GPT 3.5 Turbo to connect to our LLM agent. All the other stuff, including object detection, SLAM, 3D clustering, and ray tracing, those are all happening on CPU-based systems. And we leverage the CPU ray tracing engines to generate these 3D scenes. So we ask the LLM agent, move to the red ladder on the right. So we are asking the drone system move to the red ladder on the right. So the first it goes is, I need to use the object detector to find the object. So then use 2D to 3D to identify the 3D location. So it goes ahead, runs the 3D object detection. It identifies where the red ladder is. And once it has identified the red ladder, it goes ahead and builds that bounding box. And that bounding box allows it to place that 3D object with differentiable rendering in that scene. And once it has the object in that scene, it is able to figure out what path it needs to take and then drives to that particular scene and generates those images. So it looks at the object, figures out where the red ladder is, then decides how to plan that, then takes that drone path and identifies that is in fact the red object. So you can also take multiple pictures from the drones and do it the other way. That is, we can this is me showing how the drone starts, figures out where to look for a particular object and identifies that red ladder. And we can extend the same sequence to build the entire digital twin, which is what we have done so far using GPT Turbo, our vision system, our Lidar system, and motion path. We are now extending that work using NeRF and Gaussian splats so that we can do that in real-time 3D reconstruction. I hope this was useful. Thank you, everyone.
I think it's the time for questions. Does anyone have any questions to ask Dr. Kumar? Dr. Kumar, I have a question to you. So most of your presentation focused on identifying objects, and recent trend is there how not to identify an object. So do you work in that area as well? So you can hide or you can make your background such that person cannot be detected, or just for the security purposes and all.
Yes, like I was showing in the low income neighborhood situation where it was failing to identify objects, even though it is like clearly visible. So we do work on adversarial systems, which can hide objects or place a 3D object in the scene. Like we're looking at general 3D objects like the fire hydrants, and what if you change the location of the fire hydrants? Does it then fail to identify objects like cars which are next to that fire hydrant, not blocking it, of course. So that's another interesting aspect, but it also what we noticed was even just those are adversarial attacks, but nature plays a big effect, like haze, rain, all of those have pretty significant effect in successfully identifying objects or manipulating scenes.
So what kind of error do you see in these kind of situations, like when you do this ray tracing? So you said like the person is, the system was able to identify some objects, but those which are identified, how do you verify the correctness, like the object is the one which you are looking for?
Yeah, so we have certain objects like ladders and walls or cars, and we have 3D models of those. So what we do is we do a differentiable rendering of that 3D model and try to minimize the loss from the camera angle, which was observed. And if we can minimize and actually get to a certain threshold, we say, yes, this is actually the object that was identified. If not, we go through the library, which is like we only had a finite set of library of like 500 objects. Of course, in the real world, it's going to be a lot more than that. And we need to be able to compare against which object it is. And we started by picking the most likely object and then went down in order of the objects in case a car could be misidentified like a bench in a rain. So it could start with a car and then try to see if it's a bench is an actual fit of that 3D scene.
So does it like a probability distribution over the different objects which are being identified?
So we initially started with bounding box, but of course, like you can have a person and a lamppost both have the same bounding box dimensions and location. That's where differentiable ray tracing becomes useful, because now we can see if the silhouette or the camera that picked up that object matches the 3D reference model we have, and then place that 3D model in the scene and see if it makes sense or not.
And the last question which I want to ask you is regarding the in situ visualization, where You were running the experiment at the scale of 10,000 cores, maybe 1,000 nodes
Yeah.
in Frontera system or so. So in that case, did you find any difficulty in accessing the data all from the or getting the data from the scratch file systems, and then was it like a lot of file IOs and all, which was restricting your performance or go beyond that scale?
So in the in-situ visualization, we avoided writing to scratch. So the whole objective of in-situ viz was we keep the entire data set in memory. So the only challenge was trying to decide how to queue and send it to our ray tracing engine. The ray tracing engine was Galaxy, which was using like the Osprey to do the raycasting aspects of it. That was all done asynchronously and completely in memory so that we don't hit that file system. The overhead, because we had everything in memory and doing in-situ rendering, was only 2% of the entire simulation. So compared to a file IO, which was a lot more significant, like we were able to do it with a small 2% overhead in our visualization.
Are there any other questions to Dr. Kumar? You can raise your hand to ask the question verbally. We can unmute you.
Yeah, so this is David Martin. That was a fascinating talk, thanks. I was wondering if you could talk a little more about the computing requirements as you see this scaling out, and especially in remote sensing, it seems like you would run out of processing power. Are you doing it remotely or trying to connect back to central resources?
So like the compute power for differentiable rendering is like we had to do all of these on multiple nodes on Frontera. So each with the Cascade 8280 processors. Doing it on edge devices, it's going to be way more expensive. So we've been working on how to do edge computing as a separate area. So we have a project where we are investigating tiny models, but also try to do reduced parameter models to see how much compute can we actually fit in those. So most often that means instead of trying to do a full-blown differentiable rendering, we are trying to use a machine learning surrogate of that. But like currently the real-time 2D to 3D is like Gaussian splats. Again, that's a computationally intensive system where you need a GPU to run. But trying to run it on edge devices with fewer parameters is something our group is currently working on. And we are trying different approaches from reducing the number of parameters to using mixed precision. But getting into the fields, we might need a network of devices is where we are going. Even in an edge-based system, you could have devices on lampposts, people with head-mounted displays, and we want to be able to have certain things offloaded onto systems like lampposts, which can have beacons, which does the compute, to just do real-time machine learning, tiny simulators in the heads-up displays.
Yeah, interesting. Thanks.
Do we have questions in the question doc?
I don't see.
Okay. I think we are almost at the end of the presentation. Just asking at the last time if we have more questions or someone is not able to ask the questions before.
There are some questions in the question doc. The first is, did you experiment with night conditions to try to get more detection on par with daylight? Did you try a night vision sensor?
We haven't tried a night vision sensor. This was our initial part of the work. That's definitely there. Because most of our construction sites are limited to working hours, we haven't tried that, but that's a great suggestion that we will explore.
The next question is, have you thought of using a multimodal LLM like Lava for object recognition?
Yes. So, sorry, some of the work you've seen is like our past 2 years. So things like GPT-4 vision didn't exist when we were doing this. Those are something GPT-4 or Lava are something we're definitely working on right now to improve our models. Even our 2D to 3D scene, we've gone from make it 3D to using neural radiance field, and now we use Gaussian splats to do a full 3D reconstruction.
And one last question from the question doc. Did you exascale computing for your digital twin models?
The digital twin models were not close to exascale. The in-situ visualization was closer to the exascale simulation. But the digital twin, we were doing it on multi-node parallel system, but definitely not close to exascale.
Any other questions?
Thank you, Dr. Kumar, for an excellent presentation. And for attendees, we will provide the slides and recording in your inbox by tomorrow. We will conclude the webinar. Thank you, everyone.
Thank you.